Be able to have to do for the test. So let's start. So there's going to be two kind of big types of problems. One of those is going to be that photoelectric effect. So try that number 10 with the where you have light. This is the one that's like the single sheet that this is light's coming in, the electrons are getting kicked out. Try that one. If you run into Dr. Botts, thank Dr. Botts for getting me the Surface Pro because I'm much happier. Oh, you're back in the
These are assignments. Oh, Berg discovered emojis. I'm now fit. Rhombus. Makes everything better.
You just said you just this one. Just said.
I can't figure out how to spin it. I can move it. That's what I'm trying.
I think you have to hold it down and go to A.
Do what?
Yeah.
That's what you did.
Yeah.
Oh, gotcha.
thought I meant for just I don't know if that's right. What did you guys get? What did you get for B and C?
That's what I got too.
For B, wait, for B?
Yeah.
Okay, are you, so
I
are you
got
saying?
that one.
I think both me and you misread it.
I think you're supposed to use the
Because
one.
from B, you're supposed, yeah.
I think you're supposed to use the thing from B. Not
Look at
the A.
the, look at the line above question B.
Yeah. Says the
the frequency?
photon emitted during transition B. During transition B.
What are you talking about?
So, okay,
Transition
look at
B.
Look at,
the photon emitted.
No,
what problem are you on?
You should be working on this one, it has a little light shining in on the,
What?
Yeah.
What?
You said there's so many
That
sheets.
was not what we were working on.
I got the same.
You got what I got.
I got the truth.
this is the one we're gonna work on first. We're gonna get to the other ones. The one with the light shining on the metal.
Yeah, kilograms times meters per second.
I just slowed it.
Okay, why are you doing this? Yeah.
From where?
Where'd you get from one?
For what?
The frequency.
That's the
Gives you
frequency.
Gives you the waveform.
Gives you energy.
Why do you don't get half the.
That is like, this is for.
Bro, how are you?
No, you can,
What did you
you just use frequency equals the speed of light for the wavelength.
Yeah.
Why would you?
It's because that's the energy of the, because that's the energy of the electron.
Did you get 0.688?
Yeah, I got 6.875, yeah.
And it's like that.
I'm saying it won't be that bad.
I know, it's kind of good.
It's like I learned.
You just really enjoy hanging out with Miss Wilcox. And nobody enjoys that.
The head counselor at Mid South.
Huh?
The head counselor at Mid South. In Santa Claus.
Is what?
She's just not that person.
Does she not hate you? I feel like
Everybody.
Everybody hates her, but like
you're the bane of
And her
counselors
husband.
everywhere, though.
Yeah. Yeah, I like
He's
Bill
our
Williams.
SRO and we miss Officer Albert. You guys really lucked out with that.
Oh, that guy.
That guy.
Sorry.
The guy who woke up one morning and because his wife couldn't find parking because she was late, gave everybody a ticket in the parking lot and started harassing them for a week.
Wait, what'd you get?
I mean, I'm kind of happy he did because now like the gold card parking's for like gold card, but he wasn't very nice.
Oh, that's what that was all about?
Maybe your wife was
What?
For this problem, if I'm using wavelength equals h over
Wait,
e, should I use
It was
the joule seconds h or the?
I don't, it's whatever one you want.
That doesn't make sense to me.
What doesn't make sense to you?
Well, because
I guess I can calculate it. I guess.
how would I possibly get the same answer?
But because I didn't put it on my actual. There's one less person, there's one less overlap.
It doesn't ever specify that.
Instead of letting pro just take it.
Oh, no, it's because.
But even though the overlap in that would have been the same.
Connor, what did you get?
Hey, what are the units of momentum?
Yeah.
Of what?
But that was really
Is it like Newton?
Yeah, and Delver gets to go like actually do.
a really, really good.
I think it's, I don't think there's a unit for that.
Sydney,
Wow.
did you get,
Stop.
you get
Yeah.
2.41 for B?
Yes.
Okay, cool.
Nobody has that.
No,
wait,
Did you
know what
get
that may sound like a perfect
1.66
I don't know how to calculate
times
No, pull up.
10 to the negative?
Yeah, because Leona
D?
drops everything
It's
else.
just momentum equals
Not
Planck's
got
constant
super
over
water.
wave.
If you have to go get a doctor's note for
H.
drugs in the middle of the term, it shouldn't count.
There's two different H's.
Just make the,
For me.
wait, what
Do
did
you,
you, what did you?
do you have joules or do you have electrons?
What did you
Carrying your
get?
mommy that you're not gonna get your
Yeah, you're both in
period.
the
Sorry.
D,
Like,
1.66
Okay,
times
Danny, fire that up.
negative
Oh, it's been running.
Oh.
It's been running.
She got a 60.
All right, so let's talk about this problem with the light shining on it.
Did you convert?
So, part of this you have to understand on the photoelectric effect that you have two different trons. You have the photon coming in, and then you have the electron being kicked out. So when you look at your K max, which is also your voltage max, it's the same thing. That equals HF minus your work function, okay? So this part is the photon side of it. That's how much energy it comes in. This is the electron part of it and how much energy it takes to free the electron. And the difference between the two of those is how much energy it takes to stop the electron once it gets kicked out, okay? So you got photon coming in, the electron coming out, and then the capacity to stop the electron once it gets out. I'm showing up, I'm freeing Cohen, Cohen gets out, we gotta stop Cohen, okay? So, hopefully A gives you no problem at all. It's just the speed of light, the only thing you have to watch is that that's in nanometers, the speed of light is in meters. You got second. So and here's nanometers are simple because it's just 400 times
10 to the negative
9,
9.
and then you get a frequency of 7.5 times 10 to the 14 hertz. Okay, cool. As that light passes through different mediums with different optical densities, what happens to that frequency? What happens to the frequency as light passes through glass, water, whatever? Nothing. Nothing happens to the frequency.
Frequency determines color.
Because frequency determines color, because frequency determines energy. Okay? As you writhe in pain, Deacon. So, on B, you want to calculate the work function. So, there's a couple of ways you can do this. You can either stay in joules, you can work in electron volts. I prefer to work in electron volts, that's just me.
It's just bigger, it's less messier.
So, basically, your work function then is gonna equal your stopping potential minus your K max, and that's the energy of the photon. So, you got 1240
Oh, I see.
nanometers electron volts, you divide that by 400. You get that in electron volts, and then you gotta take the 1.1 times 10 to the negative 19th joules, divide that by 1.6 times 10 to the negative 19th joules per 1 electron volt, and that gets you a whopping 310 minus 0.69, which gets you 2.40 EVs. If you were old school, it's like, oh, Burkamp, I want to work in joules. If you worked in joules, that's 3.9 times 10 to the negative 19th joules. Okay, I don't care which one you work in, pick one. Okay, I usually just work in electron volts. Now, so the stopping potential is a little bit weird in how this is particularly phrased, because it says calculate the stopping potential for the emitted electrons. So, because of the fact that you're technically talking about potential, that technically needs to be in volts. So, this is where kind of you get electron volts from. So you have how much energy that it has, 1.1 times 10 to the negative 19th joules, right? So if you say, well, that's how many joules there is, and if you convert that and divide that by 1.6 times 10 to the negative 19th, okay, which is also the charge on an electron, and if you do this math, you get 0.69 volts, okay? Or, and it was weird how they graded this question, because it actually asks for stopping potential, you need it to be in volts. But here's like the deeper understanding is that if this is how many joules of energy that it takes coming out, that's also how many volts that you need, but to get the volts, you divide it by the charge on an electron, and that's why it's called electron volts, because it's the volts that you need to stop an electron, okay? Which is also the number that you got up here when you took the K max and converted that into electron volts. So if you did it this way, and you worked in electron volts, you had already actually found the answer to C because you knew what the electron volts were from the previous answer if you had worked in electron volts. So you had the answer if you already did that. Now, D gets a little bit sketchy, mainly because of the fact that you want the momentum. So this is where it's handy if you want to remember this. Remember that E also equals momentum squared over 2m. Okay. So that's one way that you can do this. If you happen to do that substitution, because kinetic energy equals 1/2 mv squared, momentum equals mass times velocity. So mass then is momentum over, or mass is momentum over velocity, or velocity is mass divided, momentum divided by m, and you do that substitution back into there. That's one way you can do it. The other thing that you can do is if you don't like that, it's a two-step process. So if you don't want to remember this in your old school, the other thing you can do is go, well, that's how much kinetic energy it has, and that's 1/2 mv squared. So you take the kinetic energy that it has, and then you know the mass of the electron, and then you find the velocity that way, and then you take that velocity and put that into mass times velocity, the old-fashioned way of doing momentum, okay? You're going to get the same answer either way. This is just a little bit easier if you remember that it's momentum squared over 2m. That's another way to express your kinetic energy, okay? I don't care. Either way you do it, you should get 4.5 times 10 to the negative 25th Newton seconds, okay? Cool with that. Now, if you wanted to, and particularly this, they didn't, but they could have, knowing that that's the momentum, what else could you find?
The de Broglie wavelength.
What'd you say?
The de Broglie wavelength.
The de Broglie wavelength. So how could you get the de Broglie wavelength?
You divide h by the momentum.
Well, lambda equals h over,
Momentum.
which would be, and then you could take that, put that in there, and then you know what the h is, and then you could find it that way. Okay, so that's the big idea on that. So let's go to that. It's at 2011, number 6, where it has the, what is it? Oh, it's that bottom number 6, because that's the hard one. So it's that bottom number 6 where it says the allowed energies of a simple hypothetical atom. And it's rare that they do that, but basically the values are negative, but that, don't get hung up on that. All they're saying is that that's a negative value relative to the electron being infinitely far away, and we brought the electron in. So don't get hung up on the negative values, the physics is still the same, you still have differences in the energy levels, okay? They're just saying, here's 0, and then you have negative, and then they just go down from there. So, now Danny, stop the camera, and try that one.